All right, it's 8:59 on my computer, so it's almost time to start. Well, now it turned 9 o'clock, so let's start. So good morning, everybody, and let's start with checking that the audio and video and things work. So if you hear me and if you see me, please type yes or okay or something in the chat. And yeah, it appears that the technology is working. Great. So today there are two topics. I think that's my plan, at least. We will talk about network slicing in a little bit more detail than we have talked about previously. And then we will discuss edge computing or And the idea with network slicing is that we somehow logically divide the physical resources into, in this case, 3 network slices. That just happens to correspond with the 3 main use cases, eMBB, URLC, and MMTC. And I think I also showed you this network slicing picture from the GSM Association. It's a bit more messy, I think. And in this example, there are also 3 slices. I think 3 is a nice number, but in this example, there's 1 slice for utilities, there's 1 slice for the automotive vertical, and there is 1 network slice for manufacturing purposes. So let's investigate network slicing a bit more in detail. So what we will do here is that, here we have the kind of physical representation of things. Hardware here means servers or compute nodes. There's a base station here. And on this side, we have a kind of more logical view of the network. And as you probably realize when you look at the picture, there will be 3 different network slices here. We will talk also about slice-related numbers. What is a slice called? How can a user equipment ask to be part of an eMBB slice, for instance? And I have a few PowerPoint presentations too. So let's start. So network slicing is about, as it says, there's creating some type of logical networks within the physical network. And the idea is that these logical networks, the network slices, have different profiles or different characteristics. For instance, in terms of traffic capacity. An eMBB type of slice for regular subscribers who are streaming audio, video, uploading things, probably needs a high capacity in terms of traffic handling. If we have a network slice for some type of mission critical services, police, firefighters, that's a smaller number of users, and maybe the need for capacity is smaller. Number of registrations or registered UEs. And if I remember from some previous PowerPoint presentation, one design criteria for 5G was that it should be able to have 1 million connected UEs per square kilometer. And many of those UEs will probably not generate that much traffic, but just the sheer number of UEs will be a challenge to the network, because the UEs, they need to be registered, they need to have identities, the network needs to store maybe mobility related information. So just storing information about all these registered UEs is perhaps the biggest challenge, not the traffic itself. Reliability. A slice for URLC, ultra reliable, low latency communication needs to be more reliable than eMBB slice. Also latency, of course. Actually, URLC, ultra reliable and low latency communication, it's really a combination of two things. And it's not necessarily always the same thing, because something can require high reliability, but not necessarily low latency, and vice versa. So that use case and the URLC, it's really a combination of two different things. Coverage. If there is a slice for handling the public transport system in Budapest, like having all the buses and the trams connected, of course that network slice only needs to cover Budapest and maybe the surroundings. There's no need to have coverage all over Hungary for a Budapest public transport type of network slice. So you can think of other types of characteristics. These were just some examples. And the way typically to create and manage network slices is to make use of virtualization and software-defined networking. So we can write up here in the box here that NFV, network functions virtualization, and SDN, software-defined networking, is typically the tools we use for creating network slices and managing network slices, and NFV and SDN are main tools for creating / managing network slices. So great. Here we see 3 UEs. We have a G-Node B. It says hardware, because at least part of the G-Node B can and probably will be deployed on generic COTS hardware. There are some things in the radio network which cannot be virtualized. The really radio close things, I mean the generation of radio signals and filters and stuff like that, it is not suitable for virtualization, but other G-Node B tasks can and probably will be virtualized. So in this example, we have some generic COTS hardware used for the G-Node B or part of the G-Node B. And then we also have other servers or compute nodes in the network. So black box like this is a server in a data center somewhere. And maybe you can imagine that some of these servers are closer to the G-Node B, like further out in the network, and some of these servers are deployed in some more central data center further into the network. And here we see 2 data networks. So what we will do is that we will create 3 different network slices, and it will be a green and blue and red network slice. So this time I will use colors for different network slices. So let's say that user equipment 1 belongs to the green network slice. So out here on the radio interface, we have some green radio resources. The GNOD has in some more or less dynamic way allocated some part of the radio resources to the green network slice. And exactly how this is done, whether it's like part of the frequency spectrum or if it's more based on some type of dynamic algorithms, that's implementation dependent. The specs actually say very little about it. But this also means that part of the GNOD, part of the radio resources, part of the memory, part of the intelligence of the GNOD is allocated to the green network slice. And I will just indicate it with a little green line like this around the GNOD. And then, as we know, we need to have network functions in the core network. A number of them. We need to have an AMF, and we need to have a session management function, and we need to have UDM, and we need to have a policy control function, and UPFs, etc., etc. Here they are just called DNF, as in virtualized network function. So let's color a few of them green, indicating that they belong to the green network slice. So as an example, this VNF here, that one belongs to the green network slice. This DNF also belongs to the green network slice. This VNF belongs to the green network slice. And also this one down here. So that's 4 DNFs in the green network slice. If you remember from earlier on, there were many more different types of network functions in the core network architecture. We had the NRF, we had the charging function, we had the 5G EIR, we have the network exposure function. So, but we have simplified things a little bit. Great. So, from the more kind of logical perspective, we have now created a green network slice. And of course, in a real 5G network, the slices will not be called green and red and blue. The slices will have some network slice instance ID, which I suppose is a number, but to keep things relatively simple here, we will talk about different colors of slices. So user equipment 1, and maybe these 3 or 300 or 3,000 or 3 million other UEs belong to the green slice. There are some green radio resources. And there's a green G node B. And we had 4 green boxes over here. So we have 1, 2, 3, 4 green boxes here. So let's do some coloring. Like that. And here it just says VNF, 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 because they are all virtualized network functions. Maybe with a bit of imagination, we can figure out what type of VNF this is and what type of VNF this is, and those ones. And yeah, this is a VNF which has an interface to the G node B, which means that it can either be the AMF, the Access and Mobility Management Function, or a UPF, because the other VNFs do not have direct interfaces to the G node B. And yeah, my idea when I did the picture was that this is an AMF, an Access and Mobility Management Function. And this is a VNF which can communicate with the AMF, and it seems to control 2 other VNFs a bit further down on the picture. So once again, my idea was, of course, that this is a session management function, and these are 2 user plane functions. And in this example, because it's obviously just an example, the green slice gives access to a data network. And if we go back and look at this picture, we have one green VNF here, which connects to data network 1. We don't have any green VNF here. So my idea, once again, because I did this picture myself, I cannot really blame anybody else. My idea is that, or was that, this is data network 1. As you can see here, a network slice can provide access to multiple data networks. So there is a kind of 1 to n relationship between a network slice and the number of data networks. But in this example, there's only one data network here. Maybe this is a network slice for eMBB, Enhanced Mobile Broadband Services, which would probably make these UEs smartphones or pads or pods or this type of equipment, which we have been using for mobile broadband since 10-15 years, and now with eMBB we get higher capacity, more resources, better experience. So let's take a quick look at the eMBB use case. Maybe you remember this type of triangle with the three main use cases in each corner. And a couple of years ago, there was a survey, and operators were asked, when you roll out 5G, what will be your first focus? So the question was, what will be your highest priority use case in early 5G deployment? And of course, most operators said that we will focus on the eMBB use case. Some operators said that we will focus on massive Internet of Things. Only a few operators saw the URC type of services as the main use case. So I suppose eMBB is to a large degree about connected people, maybe not so much connected things or connected cities or industry automation. Here's this triangle again. Enhanced mobile broadband services that require very high bit rates, maybe augmented reality, virtual reality. I think voice is definitely an enhanced mobile broadband service. In this picture, it's shown here. I think I would put it closer to the top of the triangle because it's certainly not massive machine type communications, and it's certainly not an URC service. So IMS based voice, like VoLTE, but in the 5G network, that would be a eMBB type of service. For eMBB, we will need more capacity because there will be more people, more UEs to serve. And I just collected a number of typical eMBB services application areas, everything from the very classic basic internet access over the 5G network for over-the-top services. I mean, watching YouTube, listening to Spotify, updating Facebook over the 5G network. Broadband to the home via 5G. Actually, fixed wireless access was probably the first 5G use case. So connecting houses with 5G in case there was no fixed broadband connection. If it was too expensive or complicated to have a cable or fiber to a house, 5G could be used pretty much like we use 4G routers to sometimes to connect houses or homes or apartments. We will not go through everything. I think you get the picture. So this is maybe what a eMBB type of network slice would look like. It's yellow. Maybe I should have made it green, but so this network slice is dimensioned for smartphones with typical mobility behavior. Smartphones move around like smartphones do. Maybe there will not be millions per square kilometer, but for sure hundreds of thousands. High bit rates. So the radio network has to be dimensioned for these types of users. And also the core network, the capacity in the UDM, the capacity in the AMF, the traffic capacity in the user plane function has to be calculated and dimensioned based on these types of customers and these types of services. And I suppose an eMBB slice will, of course, provide internet access. It will also, I suppose, provide IMS access and probably or maybe also access to some corporate intranet. And in this example, I have also created a second eMBB slice for maybe premium subscribers, the people who pay more, the people with expensive subscriptions, or maybe corporate customers, or maybe an MVNO, a virtual network operator. Maybe it would be a good idea to kind of host the premium subscribers or the corporate customers, some bank or insurance company, or an MVNO in a separate network slice. Fewer UEs sharing the capacity, and obviously the radio network and the core network can be dimensioned in a different way. One question which people often ask, and which I often ask myself, is like, how many slices will there be in a typical network? And I've heard some people say that, well, to start with a typical kind of public network from a traditional operator, a few network slices, because we need to understand how this works, and we need to understand the dynamics of network slicing. I've also heard other people say that, well, there will be thousands of network slices in a network. Every time a new corporate customer is onboarded, a new slice will be created. So I think we don't really know how many slices there will be in a typical network, or at least I don't know. I'm still a bit confused about, will there just be a few slices, or will there be hundreds or thousands of slices? Maybe it's too early to say. All right. Let's go back to the physical picture. UE number 2 belongs to a blue network slice. So I will use the blue pen. Oops. So in some way, the GNODB has allocated part of the radio resources for the blue network slice. It can be very static, maybe for, say, a network slice used for public safety, mission critical communication, police, fire department. Maybe there's a requirement that 15% of the network resources shall be kind of hard locked to that network slice. That would be like a static resource allocation. For other types of network slices, it might be okay, and it might also be very logical to use more or less radio resources. Yellow slice can borrow resources from the brown slice, etc., etc. So resource allocation can be either static or dynamic. This also means that part of the G0B, memory, intelligence, processing power, whatever, belongs to the blue network slice. So I will color this shape blue. And yeah, you get the picture. We need to have some blue VNFs, and this one will be blue. This one will be blue. So the same VNF can belong to multiple slices. I think some VNFs will more or less by definition belong to different slices, like this NRF, if you remember, the network repository function, which is a network function where other network functions will register, and it can be used as a kind of lookup function. Same thing with the UDM, maybe there's a common UDM for all the network slices. So it's perfectly okay for a VNF to belong to multiple slices. And I have to look on my paper. Also, this one is blue. So let's move over to the other side. And let's zoom out a little bit. So UE number 2 belongs to the blue network slice. So this is the blue slice. UE number 2. And yeah, also UE number 3 belongs to the blue network slice, so we can indicate some blue radio resources. And obviously there are also other UEs, or probably there are other UEs also belonging to the blue network slice. So this represents any number of other UEs. And the G0B belongs to the blue network slice. And yeah, just to be very clear, maybe over clear, this G0B is the same as this G0B. It's the same base station we talk about. It's just that that physical base station belongs to both the green network slice and the blue network slice. And then we have one, two, and three. The NFs, actually, we have one more here. Yeah, my intention when I did the picture was that this is an AMF, this is a SMF, session management function, this is a user plane function. I will not write it. If you have pens and papers and if you want to write it, go ahead, but I will not. Yeah, here we have a fourth VNF, which is close to the G0D, or at least, once again, that's my intention, is that this is short distance. And if we go to this picture, it's this one. I forgot it, but I deliberately forgot it earlier on. But now we can color it blue. And my idea is that this is a UPF, a user plane function, which is, well, maybe it's even co-located or co-implemented on the same hardware, on the same server that we use for the G0D. Which means that the user plane, the traffic, can be terminated very far out in the network on the RAN site where we have the G0D. And from this point, or from this network functions, there is access to a data network, and we can call it data network 3. DN3. And inside the data network 3, there are application functions or application servers, or at least one application function or application server, and there is some type of service or application going on like this. Does this sound like something we've talked about before? Yes, it does. It sounds quite a bit like edge computing or multi-access edge computing, having the services located on the edge of the network to allow for shorter latencies, and also it means that we don't have to download the transport networks further in with traffic, because we terminate the traffic already on the edge of the network. So this is a blue VNF. It's the user plane function I just talked about. And the idea is that this provides a kind of shorter or faster access out to this data network. And This is data network 2, and this is data network 3. Maybe it would have been better if I moved this cloud closer to the edge of the network too. Maybe next time I change the picture, I will move the cloud, because now it looks like the kind of distance between the user equipment and the data network, it's still the same distance. But I think the idea with edge computing is not only to move the user plane function to the edge of the network, but also the application. So data network 2, data network 3. All right. Before we have a break, let's just talk about the URLC use case. Maybe this blue slice is for ultra reliable and low latency communication. So let's see what that is about. So yeah, at least initially, only a small part of the operators saw this as the kind of killer use case for 5G. What does it say? It's in tiny font. Advanced AR and VR, connected and autonomous vehicles, industrial and vehicular. I don't know how it's pronounced. It involves vehicles, automation, mission critical broadband, for instance, emergency services. On the other hand, there's a lot of talk now about private 5G networks, or non-public 5G networks. And there's frequency spectrum set aside in many countries for private 5G networks. And I think a typical use case for a private 5G network would actually be inside some factory or production plant for industrial automation. When we talk about connected vehicles, we are not necessarily talking about cars on the streets of Budapest or Stockholm. I think the kind of self-driving cars in the middle of Stockholm is maybe still a few years ahead. But when we talk about vehicle-to-vehicle communication or vehicle-to-X communication, the vehicles can be trucks inside a production plant, fetching something from one shelf, delivering it to another shelf, fetching cardboard boxes in the warehouse and moving them somewhere else. So I think probably that type of V2X communication is probably closer than self-driving cars on public streets. Yeah, car-to-car communication, smart mobility, e-health. Once again, very often they talk about the remote surgery. Some brain surgeon in the United States operating on somebody's brain in Stockholm. I don't know if I would be too happy about that if it was my brain. But so I think some of these like remote surgery use cases are a bit futuristic, to be honest with you. Yeah. You get the picture. Very important, obviously, for ultra reliable low latency communication is the latency. And here it says 0 latency. That's impossible, but we talk about latencies, kind of latencies between an application and the application server of 1 or a few milliseconds. And that's short or low. Yeah, you see, industry automation, e-health, connected vehicles, public safety. And sometimes ultra reliability is key, sometimes low latency is key, sometimes both are required. Yeah. I picked these things from some white paper somewhere. We will not, or I will not read everything. Yeah, when an operator designs and dimensions an URLC type of network slice, yeah, how many devices will there be? What about bandwidth? What about, yeah, security requirements? Do devices need to be reachable? So there are lots of things to consider. In the end, maybe in or for a hospital, there will be a network slice, kind of purple-ish network slice. These are patients, maybe not patients with smartphones, but the UE will be some type of medical equipment measuring heartbeat or temperature or level of such and such in the blood. And this will be reported to some hospital server, an application server that gathers medical data from the patients. And I suppose it's quite likely that the hospital server is geographically in the hospital, which means that we would like to be able to terminate the traffic inside the hospital. Maybe this is also a security requirement. The rest of the core network things, the UDM and the AMF, and they can be somewhere else. But the reporting of medical data and maybe actions based on this is kept locally. Another example, let's say that these are cars. Two streets are crossing or merging, and yeah, if the vehicles are connected, maybe they will report to yeah, the vehicle manufacturer, maybe once a day, that I'm doing fine, everything works like it should, and or maybe the car will report that I have a problem, I need maintenance, maybe not immediately, but within the next week or so. Or maybe these cars are reporting to the smart city traffic planning application server. I am in this position, I am moving with speed such and such in direction this and this. And if all cars, or sufficiently many of the cars, are reporting that information to the smart city traffic planning application server, maybe traffic can be redirected in some way to avoid traffic jams or warnings can be sent out. Yeah, you can imagine different use cases for this. Great. Let's have a 10-minute break and then we will continue. So as usual, I will set the timer for 10 minutes and see you in a while. All right, time to continue. And yeah, of course, there will be a red network slice here too. So let's look at that. As indicated, UE number 3 also belongs to the blue network slice. So we can, I will color this thing blue. But then we also have a red network slice. And user equipment 3 belongs to both the blue and the red network slice, and that's perfectly in order. A user equipment can be registered in multiple slices at the same time. I think it's up to 8 slices. Yeah, there's a phone call coming in, but I will not answer. I just wanted to know what it was. Yeah, there is a red. My phone is on because I have a relative who is in hospital, so that's why I haven't switched off my phone. So some red radio resources, and yeah, of course, this also means that some part of the G-Node-B's memory, intelligence, processing power, storage, whatever, belongs to the red network slice. And then we need to have some red VNFs, and as you have probably figured out, everything which is not green or blue already will be red. And yeah, also this one. Yeah, here we have a server which does not contain any virtualized network functions. So does it mean that somebody bought too many servers, or why do we have this one? Well, this could, for instance, be spare hardware capacity. If we have virtualized network functions and generic COTS, common off-the-shelf hardware, it means that we don't have to have a spare AMF and a spare SMF and a spare UPF. We can just have some spare hardware, and then we can, or the management system can start an AMF or a UPF or a session management function here. The reason why this is empty can also be because this picture was made in the middle of the night when typically traffic load, etc., is low. But every morning when people wake up and when things start to happen, we start some VNFs in this server. So that could also be a reason. So this picture or drawing is like a snapshot picture of what things look like at a certain moment in time. Tomorrow it may look differently. Tonight it may look differently. Also, maybe next time I redraw the picture, I will make some of these rectangles bigger, because we can have VNFs which are larger in the sense of more capacity, and there can be smaller VNFs. It's also possible from a management system to scale things, so we can dynamically make a VNF larger or smaller. They talk about scaling out and scaling in, or scaling up and scaling down, depending how it's done. So yeah, over here we now have a red slice. Oops. And yeah, you get the point, I'm sure. There are some red radio resources. There is a GNLB in the red slice. But this is the same as that one and the same as that one. It's the same physical GNLB, but the capacity has been divided into 3 network slices. And we had 1, 2, 3, 4, 5, I suppose, red VNFs. And yeah, also for these red VNFs, some of them are the same as the blue one here, and maybe some of them are the same as both the blue one and the green one. Once again, there is a VNF which is shared by the blue and red slice. There is a VNF which is shared by both the blue and the green and the red slice. So how this is set up, how this is managed, how this is configured is, of course, an implementation thing. And the red slice can give us access to data network 1 and to data network 2. So over here, I will just fill in the missing numbers, which is 2 here and 3 here. All right, and maybe this is a slice for connected things like IoT things or machine type communications. You cannot really see that from the way I have designed the picture, but let's imagine that this is an IoT type of slice. And let's take a look at the third main use case, MMTC, massive machine type communications. That's one way to express it. Very often you will see MIoT, massive Internet of Things use case. For all I know, it's more or less the same thing. So yeah, smart homes, smart cities, smart buildings, multiple vertical industries. Yeah, lots of meters and sensors, and often I think kind of simple equipment. We probably do not talk about the three-dimensional virtual reality or holograms or stuff like that. We talk about, reporting some number or consumption of such and such, or status of something. Is valve open or closed? Are the lights on or off? It can be really simple things. And yeah, probably the challenge, or one of the challenges, will be the number of things. And there are different forecasts about how many things there will be in a couple of years, and I think the truth is that nobody really knows. But as you are aware, we expect to connect more or less everything in the future. Yeah, this is just a list of standard development organizations and alliances for IoT. So obviously 3GPP and the mobile industry are not the only ones working with this. There is, as you can see, a huge number of other groups working with the connected things world. Yeah. Automated shopping. I think that sounds dangerous. At least if you have teenage kids. Yeah. And actually, if you take a look at this, you will find out that, do we really need 5G for having connected alarms? Do we really need to have 5G for payment terminals or vending machines? No, of course we don't, because a lot of things are connected using 4G or 3G or even 2G. So, but once again, it's the number of devices which will be the challenge. Yeah, more of the same. So when dimensioning, designing a slice for massive machine type communications, you would have to look at the kind of expected UEs and the use cases. Lots of devices, many of them will be in places maybe where you cannot charge the battery every night like most of us do with these things. There will be UEs in forests and on mountains and maybe below water and or below ground or in basements. So battery lifetime is sometimes important. And if you want the battery to last for 5 or 10 or 15 years, you have to make sure that you make life as easy as possible for the user equipment. If the user equipment has to read system information, monitor paging, send status checks and pings, the battery will be gone very quickly. So many of these connected things will basically go into some type of sleep mode for hours or even days, and then occasionally wake up and report something and then go back to sleep mode. Yeah. Do devices need to be reachable? And there is something called MICO or MICO mode, mobile initiated communication only. Yeah, it says here, which means that when a user equipment is in MICO mode or MICO mode, it cannot be paged. It will not listen to paging. It will not respond to paging. So communication can only be initiated from the mobile side, from the UE side. All right, this is an idea of a network slice for utility meters, water meters, gas meters, power meters. Many of them, some of them may be directly reporting, some of them are connected to some type of IoT gateway. So this is the UE, and the actual individual meters are behind the user equipment. And once again, yeah, radio network, core network has to be dimensioned to fulfill the requirements for this type of traffic. Object tracking example, you can imagine some logistics company that want to know where their cars or containers or boxes are, and yeah, with some regularity, UEs inside the cars or boxes or containers will report to the logistics company coordinates or some other type of tracking related information. All right. So what we will do in the lower part of the picture is to take a look at some slice identities. Because like I said, in the real world, the slices will not be named after colors. The slices will have other identities. Yeah, this is some type of slice data model, if you like. let's go back and take a look at an old PowerPoint. The registration, and when a user equipment registers, it will send a registration request. It will go to the radio access network. It will continue into the core network. And I said yesterday, or maybe it was 2 days ago, that inside the registration request, there is some network slicing information. It says here, requested NSSAI. And when I showed this PowerPoint presentation the first time, I said, don't worry about it. This has to do with network slicing. We will talk about it later. So later is now. So we will see what does this mean, NSSAI. NSSAI means Network Slice Selection Assistance Information. So it's information which is used by the network to select a suitable network slice. Or network slice selection assistance information. This information will assist the network in selecting a network slice. It's not the network slice itself, because NSSAI is sent from the user equipment. And we cannot really expect each user equipment to know how many slices there are in the network, and even less, the UE will not know what these slices are called. So what the user equipment will send is network slice selection assistance information. I would like to belong to this type of slice. And then the network will select exactly the right slice. It's a bit like, well, in the good old days when we could travel and live in hotels before this Corona thing started, you could book a hotel room and you could ask for like a business room or a double room or a family room. You normally did not book room 704 or 243 because you don't know what the rooms are called. You don't know what the numbers are, but you can request a certain type of room. And this is basically the same idea. The user equipment will tell what type of slice it wants to belong to, and then the network will put it inside the right slice instance, which is the correct word for it. So network slice selection assistance information consists of single network slice selection assistance information, SNSSAI. And we can view this as, well, once again, it's not the identity of the slice. It's a reference to a type of slice. Can write like this. And the purpose, once again, is to help the network select a suitable slice for you. So SNSS-AI consists of, well, it's a parameter. It's a number or numbers. First, there is an SST value, slice service type value, which indicates the type of desired slice that the user equipment wants to belong to. So we can write like this, indicates. And last time I checked, there were 4 standardized values of SST. And SST value 1 is for an EMBB type of slice. Standardized here means standardized by 3DPP, which means that in all networks that comply with the 3DPP specifications, SST value 1 means an EMBB type of slice. SST value 2 means URLC. Ultra reliable, low latency communication. And you have already guessed it. SST value 3 is for MIOT. Massive IoT is what they write in the 3DPP specifications. And of course, this corresponds to the MMTC use case, massive machine type communications. And there's actually also a standardized SST value 4, which is for V2X. Vehicle to something else. X can mean vehicle to vehicle, or vehicle to pedestrian, or vehicle to infrastructure. But communication involving at least one vehicle. These are standardized SST values. Then it's perfectly okay for an operator to use operator-specific SST values. So we can also write a comment that 127 127 to 255 are operator defined. So in Sweden, if we want to have a network slice for cross-country skiers in northern Sweden, it's perfectly okay to define such network slice. In the United States, if they want to have a slice for cowboys, they can define, or a US operator can define a SST value for the cowboy slice, or yeah, you get the picture. And then there is the possibility also to distinguish between different eMBB slice. I think in the PowerPoint presentation I said that there was one eMBB slice for kind of normal subscribers, and then there was another eMBB slice for premium subscribers, people who pay more, or maybe corporate customers. So we can extend the SST value with a slice differentiator. And as it says here, it's optional. And the point here, it allows us to differentiate between slices with the same SST value. That's single network slice selection assistance information, and I have tried to indicate different layers here. So each layer represents one single network slice selection assistance information. A group of up to 8 SNSSAIs makes up NSSAI. So NSSAI simply means 1 or 2 or 3 or up to 8 of these single NSSAIs. Group of up to 8 SNSSAIs. All right, so let's go down to this corner. When a user equipment registers in the network, and also when it sets up a session, it will indicate to the network slice selection assistance information. So we can write like this: user equipment can include NSSAI at if it does not include any NSSAI, if that field is empty, there is some type of default slice configuration. So UEs that don't say anything, they will be put in the kind of default network slice, or in a network slice or type of network slice which is defined for them in the UDN. We will come back to this in a little while. So if a user equipment registers and indicates some single network slice selection assistance information like SST value. No, I will start here instead. Okay. The actual network slices in the network, like I said, it's not called the green slice and the blue slice and the red slice. They have network slice instance identities, which is a number. It's a number of bits. I can't remember how many, but it's and really, when we talk about a network slice, we should talk about the network slice instance, because each slice that we have in a network, it's called a network slice instance. That's a unique defined slice with its own unique network slice instance ID. And let's say in this example that there are 5 network slice instances in the network, each one of them with a network slice instance ID. And I will simplify things a little bit and say that the ID is A and B and C and D and E. And let's assume also as an example that this is an EMBB type of slice. Network slice instance ID B. Okay, that's good enough. Is also an EMBB slice. Same type of slice. Network slice instance ID C is an URLC slice. Oops. This was a bit tricky. I don't know why. Ah, perfect. Almost perfect. Slice D is an MIoT slice. And slice E is also an MIoT slice. So once again, a user equipment will include, or at least can include, network slice selection assistance information at registration. If the user equipment sends an SNSS AI value, and the SST value is 1. It means that this user equipment wants to belong to an eMBB slice. It has no preference what eMBB slice it wants to belong to. It says, I'm happy if I can register in an eMBB slice, which means that the network can select either this one or that one. The user equipment is happy in either case. Another user equipment registers and sends single network slice selection assistance information and indicates SST value 2. And well, since we only have one slice of the right type, the user equipment will be registered in network slice instance ID C. Yeah, you get the picture. Some other user equipment sends this NSSAI slice service type equals 3, but this user equipment also adds a slice differentiator number, like 1, for instance. And it means I want to belong to an MIoT slice, but not just any MIoT slice. I would like to register in this type of MIoT slice, or this particular MIoT slice. So this kind of points directly to that slice, or slice instance, I should say. While yet another user equipment just indicates SST value 3. I will. It's good enough. And yeah, since the user equipment has no preference, it's up to the network to choose the network slice instance, and the user equipment will be placed either in slice instance D or in slice instance E. So there is obviously some network slicing information which is related to the subscription. So in the UDM, if you remember the Unified Data Management, the subscriber database, there is network slicing related information. What network slices or what type of network slices can a user equipment or can a subscriber use? We can just indicate up here that there is some network slicing related data. What the GNOD will do is to select a suitable AMF, and in this picture it looks very simple because there's only one to choose between, but remember, in a real network there may be multiple AMF instances. You can imagine in some Chinese network there may be lots and lots of AMFs, and the GNOD will select one which it at least thinks is good. Good meaning that it belongs to a suitable network slice instance. So, selects initial. AMF. This is what the can do like this. So the registration request will go to the AMF, and the AMF will contact the UDM and pull the relevant part of the subscription profile. It will of course verify is this in line with what the subscriber data says. So some type of verification will be done. So verifies, can write like this, NSSAI with, what does it say in the subscriber data? And it will also check is there a suitable network slice instance available. Like I said, if a Swedish cross-country skier goes to Denmark and wants to register in a network slice for cross-country skiers, there may not be one because they usually don't have snow in Denmark, so there's no reason for having a skiing network slice in the Danish network. So there's of course no requirement that all network slices or all network slice instances shall be supported all over a country, and even less in other countries. So is this slice type available? Availability. And is the AMF part of the selected slice instance? Remember, the GNOD makes an initial selection, but maybe the AMF doesn't belong to that slice instance. So in the end, somebody will have to pick an AMF that really belongs to the correct slice instance, and also of course select a session management function and a policy control function which are part of the right network slice instance. And this is why we have the network slice selection function. So the NSSF, we can make a little line here. The NSSF will in the end select network functions belonging to the selected network slice instance. Selects network functions belonging to the correct or selected network slice instance. Oh, a question. Can the NSI, can the network slice instance established dynamically based on the SST and SD requested by the user equipment? That's interesting question. Is it possible, if I understand the question correctly, if and when a user equipment requests some NSS AI, that the network on the fly configures up such a suitable network slice? I think I've never thought about it, but my qualified guess would be that for sure it's possible. It sounds like a policy decision by the network. If to do this or not, but I'm pretty sure that technically it's possible to kind of on demand set up a network slice instance when a user equipment asks for that. I think also remember a 5G network can be the China Mobile network or the China Telecom network with hundreds of millions of subscribers, like a public Chinese 5G network. But a 5G network can also be a private 5G network, maybe inside a factory or hospital, maybe even owned by not the telecom operator, but the factory itself. So I think to say in general that something will be done or that it will not be done is a bit tricky, because I think often it will depend on, are we talking about the China Mobile or China Telecom public network, or are we talking about a small private network inside a hospital, factory, campus maybe. I think actually if you are clever enough, you can build your own 5G network inside your house or your apartment. 5G, well, we can use unlicensed frequency spectrum. You don't really need to have a license to operate 5G, because I think by definition you can always use unlicensed frequency spectrum. So if you are clever enough and if you know how to deploy virtual machines inside a laptop, and if you manage to build a little G-Node B from things you may find in your office and you put them together, I think it's quite possible to build your very own private little 5G network inside your living room or kitchen or wherever. I don't know how to do that, but maybe some of you do. Great, 11 o'clock. Let's have a 10-minute break. I think we're quite fine on time. Let's have a 15-minute break. one 5-minute break to allow for a bit of relaxation before we start with the next topic. Great, let's start. And the next topic is MEC and LUDN, which are two different things, but they can be combined. So let's start with edge computing or multi-access edge computing. If you read older documents or maybe also newer documents, sometimes it will say mobile edge computing, and that was kind of the first meaning or the first expression. And then somebody realized that this idea or edge computing, it's not only for mobile access type of networks, it's also for fixed access. So then somebody very cleverly said that, well, if we replace mobile with multi-access, then we can still keep the acronym MEC, but we give it a different meaning. But just a little comment here that this can also or used to have the meaning of mobile, so formerly. And the general idea is to have services or applications closer to the user equipment, closer to the edge of the network or on the edge of the network. So services or applications, if you like. Hosted. Close to the user, and in our case, the user would be a user equipment. And yeah, there was a slide about that too in this long introduction PowerPoint. This Korea Telecom people picture where it says that if we distribute the 5G core, or at least the user plane of the 5G core towards the edge of the network, and if we also deploy purple boxes with applications or application servers or application functions closer to the edge of the network, that has some benefits compared to if we do it like this. Now, having said that, we can do edge computing also in 4G, and there will also be non-edge computing in 5G. Edge computing, as we'll see, is suitable for delay sensitive services and also for kind of bitrate heavy services, uploading heavy content or downloading heavy content. But for other services, there is really no need to do edge computing, neither in 4G or in 5G. I think also there was a nice Ericsson picture somewhere here. Yeah, that was the one. So applications deployed on I think what they call an edge cloud, physically in the access network. That's the way to achieve edge computing. If the applications are far away somewhere, that's not edge computing. Exactly what the edge means is very much in the eye of the beholder. I was at a 5G conference a year ago or so, and there was a panel discussion about edge computing. 3 or 4 people were discussing, and everybody agreed that edge computing was so good. And then almost at the end of the discussion, after 45 minutes, it became obvious that they had totally different ideas about what the edge means. So for one of the people, the edge was like the radio access site. It was a rooftop or a hill or very close to the end user. And for one of the other guys, edge means, well, in the right city or even in the right country. So if you are some big American over-the-top service provider, having a server in Sweden or in Stockholm or in Hungary or in Budapest, that was what he saw as the edge of the network. In some country far away in Europe, that's the edge of the network. So when people talk about edge computing and if it's important, make sure you ask them, when you say edge, what do you actually mean? Because obviously edge is not a defined word in any technical specification. All right. Fantastic picture. 3GPP specifications don't really say that much about edge computing. It's not, well, there is no MEC specification from 3GPP. The people who write specifications about edge computing is ETSI, European Telecommunication Standardization Institute. They are members of 3GPP, but ETSI is a separate standardization organization. So there is an ETSI MEC architecture, and I will show you a slide in a minute or so. The kind of ETSI MEC architecture, it's once again, it's not only for fixed access, it's also, sorry, it's not only for mobile access, it's also for fixed access. As I will show you, they have created some type of architecture with interfaces and logical functions to enable edge computing. So general architecture for edge. Computing. which makes sense in a way because also NFV, Network Functions Virtualization, is standardized by ETSI, not really by 3DPP. 3DPP define the network functions, but looking in the 3DPP specifications, it doesn't really say that the network functions shall be virtualized. If you read between the lines, you can assume that, but NFV specifications are also from ETSI. And yeah, edge computing uses NFV. We will also see that in this slide I will show you in a few seconds. ETSI also defines NFV, Network Function Virtualization. So let's see. Not really a very fancy PowerPoint presentation. It's just one slide and there's no animation. It's just like a dead picture. But this is architecture or framework or logical functions for edge computing. And I think we recognize some of these things. Here we have a UE, some type of user equipment. There's an application running here. We don't really see any 5G network here because, once again, it's not 5G specific. There is a multi-access edge system manager, OSS, operation support system, orchestration, meaning starting things and moving things and stopping things and making things bigger and smaller, and that type of network management type of activities. There is a ME platform manager. There's a VIM, a virtualized infrastructure manager, that manages the virtualized infrastructure. And if you are familiar with the NFV specifications and from ETSI, you will recognize for sure the VIM. I think you can. Well, you will see similarities here. Anyway, what we have here, I think this is the interesting part. I will zoom in. NFVI refers to NFV infrastructure. These are the physical hardware things, the COTS hardware things, which we have talked about before. Compute resources, storage resources, networking resources, and using the NFV infrastructure and using some virtualization technology. If you remember, either virtual machines on top of hypervisors or containers, if you remember those slides from earlier, we can deploy ME applications, multi-access edge applications, as virtualized network functions, just like we can deploy the 5G core network things as virtualized network functions. Remember, AMF can be a virtualized network function. SMF can be a virtualized network function. It's some software package spinning on compute, storage, and networking resources. So using the same approach, we can also start and stop and move and scale ME applications, multi-access edge applications. So yeah, very generally speaking, if applications are far away deployed in some central core, some data center, it can be on the public internet, it can be in some other data network, and users, not necessarily 5G UEs, but laptops or TV sets or any type of terminal want to use services here. Well, latencies may be quite long. Also, the transmission or transport network here and whatever network we use here is likely to be downloaded with the traffic. If we are watching Netflix or HBO or some other streaming service, I mean, it's unicast. So for every person in the block who watches the same episode, it's unicast from some streaming server somewhere. So this could potentially lead to long latencies. And long here simply means longer than short. I cannot give you any number for what long exactly means. And there's a risk that transport networks in different places in the network will be downloaded. Transport network congestion risk. So typically, very often, there will be sites, physical rooms or places with equipment closer to where the users are. There will be kind of aggregation points for traffic. There will be network equipment in rooms, and why not move the application server or take a copy of the application server and start a copy somewhere closer to the subscribers. And this is what we would then call a MEC application server. And yeah, you get it, of course. If people can stream down video or music or content from some local site, typically latencies will be shorter, and at least this transport network will not need to carry all the unicast traffic. So low latencies and no need to congest transport. At least not this transport network. We can say that this is the and this is done, of course, already today and has been done for many years in content distribution networks or content delivery networks, CDNs. And obviously, if you are streaming down some new episode of some popular Netflix or HBO or whatever series, you're not streaming from some application server far away. Popular content is cached in lots of local content servers closer to the UEs or the endpoints. So this is, of course, already done today. For instance, for distribution, caching of some popular media in so-called CDNs, content. Is it content delivery networks or content distribution networks? I have to look if it's in the acronym list. Well, on my paper it says content delivery network. I'm still not sure because I was the one who wrote that in the acronym list, so it doesn't really matter that much. CDNs. All right. If we put this edge computing thing into the 5G world, it would look something like this. So when a session is set up, the session management function that manages the session will select a user plane function on the edge of the network. So this gray box here represents some local or distributed data center where we have hardware, COTS hardware, general purpose IT hardware. We will use some of it for the GNode B. I will come back to this later on, but we can also use the very same COTS hardware to start a UPF in the shape of a virtualized network function. So UPF. So when the session was set up, or maybe in the middle of the session, remember a session can change its topology during the lifetime of a session, like we discussed yesterday. We can install uplink classifiers and branching points, and yeah, we can kind of change the anatomy of a session on the run. But at some point, the session management function has decided to use this UPF, which is on the edge of the network. So SMF selects a UPF, which is close to the user equipment. And once again, there is no exact definition of what close means. And also, the UPF preferably has an interface to the data network. This tiny short black line here represents the N6 interface, if you remember, the interface on the outside of the 5G system into the data network. So this UPF has SMF selects UPF with N6 interface to data network X, Y, or Z. So not only do we have the UPF here, we also have the data network, or at least a part of the data network. And we can, as we saw in the PowerPoint slide, start a MEC application or MEC application server as a virtualized network function using the same COTS hardware resources, which we use for the GNOD and the UPF. The same compute, storage, networking resources can also be used for hosting some MEC application. Which means that the PDU session itself, the user plane, at least of the PDU session, will or actually the PDU session stops in the UPF, but the kind of end-to-end application can be, well, can be kept locally, or the green line is short or delay will be low, however we like to put it. So the idea here, once again, is that both the GNOD, or at least part of the GNOD, the UPF, and also the application server itself runs on the so-called NFVI, the NFV infrastructure. GNOD UPF and MEC application server run on NFVI or COTS hardware, if you like. It can be on the RAN site, like I have kind of indicated here. So the GNOD is more or less co-located with the UPF and the application server. That's one way to do it, but once again, there is no strict definition about what the edge actually means. So in this conference I attended a while ago, for one of the panelists, the edge was not necessarily the RAN site. The edge was, yeah, in the right city or maybe even in the right country. So distributed, but not necessarily on each rooftop where we have GNODs. But not. This is, of course, an optimization exercise for this MEC architecture and this MEC platform manager, and I suppose also for the 5G network. How many viewers of a certain Netflix episode do we need to have in Budapest before we start a Netflix application server somewhere in Budapest? What triggers a MEC application server to be started or stopped or even moved? And I don't know, maybe there will be clever artificial intelligence or machine learning or those kind of technologies used to manage start and stop and move and scale these application servers. And once again, when we talk about edge computing, we talk about the green line. I mean, this is where we want to have a short latency. This is where we have possibly some heavy content, very bandwidth demanding context, and we want to keep the user plane short. The session management function and the AMF and the policy control function and that can be far away. Does not need to be at all on the edge of the network, because we are not worried about the delay for registering and for the session management function to talk to the UPF. This is not delay sensitive if we talk about millisecond latencies. The low latency refers to the green user plane part. And the reason why the session management function decides to use a user plane function here, well, the SMF has some knowledge or gets some input to do this. Based on input from, for instance, the policy control function. It can be from the user plane function. It can be from the application function itself, either directly or via this network exposure function. This was basically what I said yesterday. If we go back to this picture, and we said that the session management function makes decision. Oh, it's typo here, but who cares? SMF makes decision to add release a UPF based on input from the user plane function, the AMF, the application function, policy control function. We didn't write that, but that's the idea, that the session management function will get information. Of course, it will also have its own pre-configured information, but the SMF will get information from other network functions, kind of suggesting that maybe you should choose a UPF on the edge of the network, or you should add a new UPF on the edge of the network, because that's a good idea in some way. So when and why is this a good idea? For instance, information content, which is kind of by nature local, if this is inside a factory and the kind of production server kind of supervising the production of steel or cheese or ice cream or cars or whatever, that's by nature a kind of local application. Same thing, I think there was a hospital in some example. I suppose if there's a server which collects medical information from patients and equipment inside the hospital, I think that's more or less by nature a kind of local thing. So why not try to keep the user plane local? So locally produced or consumed content. I mean, if it's produced on the edge of the network, if it's consumed on the edge of the network, why not have the application on the edge of the network? It can be for yeah, manufacturing, it can be hospital, it can be some commercial content. Maybe if you go to a sports event, you will be able to watch replays on your smartphones or pads or pods. That's like kind of local content. So commercial, manufacturing, etc. Dot, dot, dot. Latency sensitive applications, obviously. So virtual reality, augmented reality, often communication involving cars. If we actually talk to vehicle-to-vehicle communication for collision avoidance and stuff like that, if there are too long delays, there will be collisions. So VR, AR, virtual reality, augmented reality, V2X. Etc. Dot, dot, dot. This type of caching of popular media, like heavy content, high definition audio, video, in order to offload transport network resources, we typically want to cache heavy content closer to the viewers or listeners. Caching of popular media. And a fourth example could be maybe the Mech application server does some pre-processing of information. Maybe the UEs are meters or sensors or other kinds of things which will report something. And then here we will have some type of IoT gateway or whatever name we give it, which will collect all the individual measurements or reports, will maybe do some filtering, will put 1,000 individual reports into one file, and then a single file will be sent to the power company or water company instead of 1,000 or 1,000,000 individual little small reports. So some type of pre-processing of data, and it could be called an IoT gateway, for instance. All right. So that was a short description of edge computing, which is some sense about doing things locally instead of having centrally deployed applications. The second thing we will talk about in this part of the course is something called a local area data network. And as you can figure out from the name, this also has to do with kind of local services. This will be quite short, but I think let's have a 10-minute break and then we will do this. And I am absolutely sure that today we will finish before 1 o'clock. In fact, I will make a promise. I promise that we will be finished before 1 o'clock today. But 10 minutes, fresh air, fresh coffee, whatever. Huh? What is it? All right, let's continue. I think as everybody else, I'm following the election in the United States. That's the kind of the other big global interesting event that happens today. First of all, we have the 5G system overview course, and then we also have the US election, and I think we are all kind of multitasking a bit. Great. So a local area data network. Is, well, first of all, these are cells, 5G cells. And as you probably know, cells are grouped into larger areas. And just like in 4G, a number of cells grouped together is called a tracking area. So these are tracking areas, or simply TAs. All right, then we can group a number of tracking areas into a larger area, and there is a gray line indicated here. We can, or I will use the blue pen, and I will try to follow the line. Goes quite well. So the area inside the blue line is something which is called a LAN service area. So what is the LAN? Well, it's short for local area data network, obviously. But the meaning is that a local area data network is a data network, like the data networks we talked about before, but a data network which can only be reached from inside the local area data network service area. So I will change to black. A DM, as in data network, which is only reachable from some tracking area or possibly tracking areas. It can be one single tracking area, and one tracking area can be one single cell. It's a network planning thing, obviously. So a London service area can be really small, or it can be slightly bigger. So some examples, maybe inside a sports stadium, if people who watch a football game or whatever, because they're paying a lot of money for the tickets, maybe the stadium allows them to watch special content, replays of situations or background information about players or whatever, but they can only do so if they are inside the stadium. People outside the stadium will simply not be able to connect to the stadium data network. So some type of event arena or maybe a university campus. A factory data network, and for not least security reasons, the UE needs to be inside this blue area in order to connect to the factory production data network. Or a hospital, if you like. There was a student once who said that, well, actually, isn't a hospital a type of factory? I mean, you produce healthy people. The input are unhealthy people, and then the output is healthy people. It's a nice way to look at it. Or a smart city network. Once again, if all the public transport, buses and trams in Budapest are controlled by some public transport application server, maybe they can only connect to the Budapest smart city network if the geographical area is Budapest or Greater Budapest. There is a limitation. A local area data network can only be reached from 3GPP access, because the area is defined by tracking areas. This means if you are using non-3GPP access like Wi-Fi and fixed broadband, you will not be able to connect to a local area data network. Only available from 3GPP access. Okay, how does a user equipment know which local area data networks are available? Well, kind of as usual, the network will need to inform you is that where you are right now, local area data network X, Y, and Z are reachable. So AMF informs UE about LUD avail Yeah, I managed to squeeze it in. I suppose the user equipment can ask. I don't think the AMF will kind of by default just inform all the UEs about the local area data network. So I suppose it's a request response procedure. Yeah, there can be local area data networks which are open to anybody, provided that you are inside this area. And of course, there can also be local area data networks which are restricted to certain UEs, for instance, the factory or hospital network. So access to LUDN can be open or restricted. Which makes sense, I suppose. All right, so there are some simple network diagrams here. In the first example here, this is the LUDN service area. I will use the blue just to color the line. It doesn't really mean anything, but it's a nice color. So in the first example, everything, the radio network, the core network, and the local area data network itself are located inside the LUDN service area. Like this. Locally deployed. Inside the LUDN area. Over here, yeah, this is somewhere else, but in this first example, there is nothing somewhere else. Everything is inside here, but we can write the title here. Great. So what we have done here is that we have a complete 5G system, and we also have the local area data network itself deployed. It can be isolated from the rest of the world. Maybe this is a nuclear power plant or some other sensitive production environment, and basically we want to have a isolated 5G network and a data network kind of isolated from the rest of the world. So one example of this is a complete isolated, maybe private Fauci system in factory, hospital, etc. And this is a combination of a local area data network and edge computing, because if everything is local, the UPF is close to the UEs and the G-Node Bs, and if we also have the data network itself geographically, physically close to the UEs, I mean that's the meaning of edge computing. So this is a combination of a local area data network using multi-access edge computing. Another scenario is that we have the base station and the user plane function, and also the local area data network itself inside the factory or hospital or campus. This is still the border of the local area data network service area. But in this example, the AMF, the SMF, and UDM, and policy control function, and all the other cool network functions we have talked about earlier, they can be somewhere else. Maybe this is a factory or a hospital who contacted some telecom operator and say that we have heard about 5G and we think it sounds like a great idea, but we don't really know anything about 5G, and we for sure don't want to buy and manage our own 5G network. Can you please put some 5G equipment inside our factory? You own it, and put the things we need to have in our factory here, and where you have the rest of the things, that's up to you. So this is a slightly different approach. This is it's still a local area data network, still using edge computing, but maybe this is the network itself is owned, managed, controlled by a telecom operator rather than the company itself. Actually, you cannot see from any of these pictures who owns the network. So I'm just kind of inventing examples here. And yeah, of course, the third example here, inside the local area data network, we have, no, obviously the UEs, because the UEs need to be inside this area to be able to use and contact the local area data network. The base stations need to be inside the area, but the rest can be somewhere else. AMF, SMF, also the UPF can be somewhere else. Also the data network itself, where you have the application server, application function. Well, if the application is not latency sensitive, and also if we don't worry about downloading the transport network here and here with the heavy content, why not have the core network things and the data network somewhere else, maybe in a data center in far away, maybe in a different country, maybe in northern Sweden, where they build a lot of data centers now because it's cold, which means that the cooling is more or less for free. So this is still a local area data network if it can only be reached from inside this blue area, but there is no edge computing involved here. So we can just indicate here that this shows a local area data network, but no multi-access edge computing. All right. How good or bad is the idea of local area data networks? Once again, we don't know, or at least I don't know. Maybe in a couple of years, we will say that the big benefit of 5G, that was, well, it was not new radio, it was not about virtualization. The kind of killer thing in 5G was the local area data networks. Or maybe we will say that, in the beginning, there was something called local area data networks. Nobody ever used it. It turned out to be a bad idea, so everybody forgot about it. So I think it's too early to say, but this is a feature or a possibility in 5G, which I think it's interesting. I can definitely see some nice use cases for it, but once again, we have to wait and see. All right, this was my plan for today, and we are a bit ahead of time, which I think is good for everybody. Tomorrow we will shift focus a little bit, and we will move out into the radio network and take a look at the radio network equipment and protocols and new radio itself. But I will not start that now because there's only 25 minutes left, and I think this is actually a nice time and place in the course to stop for today, and then we will start with new things tomorrow morning. Great. Thank you for listening and watching, and see you again tomorrow morning.